for today's training. The second webinar of this series will go live on June 18th, and it's about the trend of flammable refrigerants in commercial refrigeration. This is an extremely important topic for everyone who will work with this kind of equipment. Our speaker, Matt Sob, will explain how to be prepared and safe when working with natural refrigerants. We are very happy today because we have many subscribers for the series, for today's webinar, and also for the natural refrigerant ones. And you will have the opportunity to watch this webinar again and share all the trainings that we are promoting later on the same YouTube link. Danny Martin, our speaker, will go through the presentation today in the first 40 to 50 minutes, and he will answer some questions from the audience in the last 15 to 20 minutes. So you can leave your questions from now, leave your comments on the YouTube chat, even during the presentation and at the end during the Q&A, and we will do our best to reply to you when we are still live. Otherwise, we can try to reply later on via email or via chat. So it's my pleasure to present our speaker, Danny Martin. Danny is NIDE Global Appliance aftermarket technical support, and he has worked with Embraco portfolio management since 2011. His responsibilities include ensuring technical support and training on Embraco products for technicians, for wholesalers, counter sales, internal staff, and he also manages the Embraco aftermarket portfolio for North America, for US, Mexico, Canada, and Caribbean. Previous to his work at Embraco, Danny spent 6 years in counter sales for a major US wholesaler of HVAC parts and equipment. And his work experience also includes 10 years in HVACR service technician working on commercial air conditioning. So Danny, we are ready to start with you whenever you're ready.
Microphone on there. Okay. Thank you very much. I appreciate it. Yep. My name is Danny Martin, and some of the things that Stella didn't mention. Well, she pretty much mentioned my previous work experience, but I was basically for 10 years did commercial air conditioning work. But so we're at what we're going to go over tonight. This is a little overview of the things we're going to go over. We're going to go over a basic refrigeration system overview. Talk a little bit about hermetic compressors and the electrical components on those compressors, how to test those compressors, some common problems you might see in the field, service procedures, and a little Q&A at the end. And if anyone doesn't get their questions answered at the end, understand that we will try to answer them through email later in the week. So welcome everyone to Embraco Compressor Technical Training. On behalf of myself and Embraco, I want to thank everyone for being with us tonight. I know these are some challenging times, but thank you for being here. And moving on to that refrigeration system overview. This slide shows a basic layout of a very common refrigeration system with the 4 main components that you're going to see in every system. Starting at the compressor, the compressor's main job is to provide the pressure difference between the system's high and low side. And we need that pressure difference for the condensing and evaporating of the refrigerant to do the job of removing heat and delivering it to a place where it's less objectionable. One thing about a hermetic compressor, it's designed to only pump vapor. We never want to introduce any liquid refrigerant to that compressor. So, like I said, it starts at the compressor where we take low pressure suction gas. The compressor turns it into hot, high pressure discharge gas and sends it to the condenser. And the condenser is the heat exchanger where this high pressure refrigerant is condensed into a liquid. As it does that, it gives off the heat to the ambient air that's passed across the coil. So once it comes out of the condenser, we should have all liquid that's going to go down to the liquid line to what could probably be called the fifth component that should be in every system, which is the filter dryer. We always want to see a filter dryer in the system. We'll talk a little bit about that later. But once we go through that, this liquid will come to the metering device. And the job of the metering device is to decrease the refrigerant pressure and temperature, which is going to allow for complete evaporation inside the evaporator coil. So when it hits the evaporator coil, we should have it ready to evaporate completely. And the evaporator is the heat exchanger where the refrigerant gas is evaporated. And as it does this, it's going to absorb the heat from the air passed across the coil from the refrigerated space. And so we're going to absorb all that heat in the evaporator, and then it's going to come down as a vapor through the suction line back to the compressor, where the cycle is going to start all over again. And one thing to note is the condition of the refrigerant through the system. As you can see, going into the compressor, it's low pressure suction vapor, and coming out, it's high pressure discharge vapor. And then it's turned into a liquid after the condenser. So you can kind of see the state of the charge of the refrigerant as it goes through the system. So this slide shows a condensing unit. And what is a condensing unit? It's basically the complete high side of the refrigeration system, containing the condenser coil, the condenser fan, the compressor. In some systems, you'll see a receiver, which is just a refrigerant storage tank, usually used in systems with TXV valves or for larger commercial systems that have large charges, and you need a little bit extra space to store that refrigerant in the off cycle. And typically, a lot of your condensing units nowadays they have service valves to isolate the system for service. And then you're also seeing a lot the dryer and the sight glass already mounted on the system. So basically, and beyond that, your liquid coming out of the condenser is going to go to the evaporator, and that's where the expansion device is going to be. So basically, it's the whole high side of the system. So moving on to hermetic compressors. What is a hermetic compressor? It's basically just a sealed unit, which is composed of an electrical motor, a positive displacement pump, and the oil. And the electric motor, it also operates in the same atmosphere as the refrigerant, as refrigerant suction gas is usually used to cool the motor, along with air drawn across the shell by the condenser fan. So basically, these are sealed. You cannot open them up for service. So a little bit about that positive displacement pump. Basically, you have a piston and a cylinder, and it's just like a piston and cylinder inside a car. It's going to draw in suction gas on the downstroke, provide compression on the upstroke, and then the discharge, the valves are going to deflect to provide compression. It's a positive displacement pump, and what this means is anything that this pump pulls in is going to try to compress. This is the reason we never want to introduce any liquid refrigerant into the cylinder or the valves, because liquids do not readily compress. If we bring in a slug of liquid to this pump, it's going to try to compress it, and it's going to cause catastrophic damage in the form of bent or broken suction or discharge valves, blown out suction or discharge gaskets. If we get enough liquid in there, we could even blow a hole in the piston or break a connecting rod, cause major damage like that. So you can see extremely high pressures inside this cylinder in the neighborhood of 3,000 psi if you pull liquid in there. So that's why we cannot have liquid in a positive displacement pump. Always want to protect these types of compressors from liquid floodback or slugs. So this slide just shows the internal, an internal view of a basic hermetic compressor. You can kind of see how the components are laid out here. We have the motor, the stator core that sits horizontally, and the shaft that goes up in the center going vertically up through the rotor to the reciprocating assembly, which is sitting horizontally. So you can kind of see the discharge muffler, suction muffler. The cylinder head is right here. Most all of our compressors, actually all of our compressors right now are single cylinder. So this is pretty much going to be the layout of all the compressors that we have today. So one of the main parts, of course, of the hermetic compressor is the shell. And it has a simple job, but basically it's hermetically sealed, so it contains a refrigerant, contains everything inside the system. But one of the things it does, it also attenuates the noise generated by the pump. And Bronco and other manufacturers spend a lot of time designing this shell to keep that the noise generated by the pump as quiet as possible. But it also mounts the suspension system. It allows for external supply of electricity to the motor and contains the lubricating oil. So one of the items you might have seen in there was the crankcase. Its main function is it holds the cylinder bore, it holds the bearings for the crankshaft, the suction and discharge mufflers. It mounts the suspension to absorb start and stop vibrations, and it provides a structure to support the pressure load. And it also mounts the motor stator. So about that suspension system, basically it's there to absorb the vibrations generated from the start and stop of the compressor. Some people think it's designed to protect the compressor from shipping forces. It is not. It's only there to absorb that vibration from starts and stops. If anyone's ever handled a hermetic compressor and you hear something knocking in there, that's the crankcase knocking against the inside of the compressor shell. Once it does that, you have exceeded the design limits of the suspension system. So if we ship a compressor like this in ground shipping, it can very easily damage it. The shocks and drops and tumbles of ground shipping can very easily damage this compressor, even if they're packed very well. So this is a better look at the motor inside the compressor. You can see the stationary part, the stator that holds the windings of the compressor. And inside that, you have the rotor, which has the crankshaft going through the center of it. So the stator generates the magnetic field to move the rotor, and the rotor transforms the electrical power into mechanical power through the crankshaft to the reciprocating assembly. And you can see how the stator is orientated in this motor here with the rotor inside of that. And there's an air gap in between that rotor and stator. We must maintain that air gap. That's one of the reasons ground shipping is very bad for a compressor. It's very easy to damage that air gap if you drop a compressor like this. In this slide, you can also see the crankshaft coming down into the lubricating oil. It has a little venturi in the bottom of it, opening there, that as it spins, draws oil up through the crankshaft and delivers it to the bearings of the reciprocating assembly. So one of the other items we have in our compressors, it's not in every compressor, it's mostly in the 404A commercial compressors that run a little bit higher discharge pressures. but it's an internal pressure relief valve, and it's a passive high pressure safety that protects the valves in the compressor from a very high discharge situation. Anytime you have suction or a pressure differential between the suction and discharge that exceeds 435 psi, this valve is going to open and relieve that pressure to the low side inside the compressor shell. It's going to make a pretty loud noise and hopefully cause the owner of the equipment to call for service. And basically what this is going to do is it's going to save the compressor from, damage. And so hopefully the technician is going to come out, correct the reason for the high discharge pressure, and the compressor will still be perfectly operational afterwards. But it opens up under high discharge pressure, and once that pressure falls off, it's going to go ahead and reset and close. Moving on to the types of motors that we use for these compressors. They're a little bit different than if you have technicians out there that are used to working on larger AC equipment. This equipment these motors are a little bit different. They have a little bit different components on them, but one of the most common types of motors that you'll see, it's actually the RSIR motor. Sorry for the missing R there, but that means resistive start, inductive run. Basically, what this means is you have no capacitors, no start capacitor, no run capacitor on this type of motor. It's a very simple motor used in small systems that use fixed orifices like capillary tubes. So it's a low starting torque motor by design. And the point here is you have no capacitors on this type of motor. Basically what this motor does is it starts out, and we'll talk a little bit more about the electrical components, how they do it, but they energize both windings, the start and the run winding, to get the motor started. And once the motor starts, they de-energize the start winding, and the motor runs just on the run winding. The next type of motor you'll see is a CSIR, capacitive start inductive run. So we have an added start capacitor. It's not just an added start capacitor, it's a little bit different start winding. Combined with the different start winding and the start capacitor, we have a high starting torque motor. And you're gonna see these used in systems that have like TXV valves that don't equalize in the off cycle. You might see these spec'd out on an application where you have very short cycling of the equipment, or just basically the system doesn't, the pressures don't equalize well in the off cycle. So CSIR has an added start capacitor and a different start winding to give it high starting torque. Then we have the RSCR, so it's resistive start, so no start capacitor, but capacitive run. So we have an added run capacitor. And basically what we're doing, this motor is still low starting torque, but it has an added run capacitor giving it a higher running torque. So basically what they're doing here is they're giving that motor higher running efficiency. So you see this motor, this is probably one of the more common motors you'll see in residential refrigerators now because of that added efficiency of the run capacitor. This is about the most efficient motor you're going to see until you get to the three-phase DC motors that you're starting to see on some of this newer equipment. So basically, RSCR just has a run cap. And then we have a PSC. This is more of your air conditioning motor. PSC stands for permanent split capacitor. So it has a capacitor that's mounted. It's actually mounted in the start winding. So basically both windings are energized at all times. But this added run capacitor, it's still a low starting torque motor, but the addition of this run capacitor gives it just enough torque to start with a fixed orifice. Since we're talking about air conditioning, you're talking about a piston typically. A lot of your newer air conditioning systems are using TXV valves. So with this type of motor, you would need to add a start relay and a start capacitor if you had a TXV valve, or some of the TXV valves that they use for air conditioning are externally equalized that help the system equalize in the off cycle to get around that. Or a lot of the compressors nowadays are using scroll compressors, which are sort of high starting torque by design, because the scrolls start unloaded, and then once the compressor started, they load up. So that's kind of how we get around that. But this is more of your air conditioning motor, the PSC motor. And then we have a CSR, which is capacitive start and run. So we have high starting torque and high running torque. So we've got the high starting torque for hard starting applications and high running torque to give it better efficiency. You're going to see this in a lot of your larger commercial compressors, especially 1 horsepower and above, 115 volt. You have extremely high locked rotor amps in a compressor like that. So they're going to use that start cap to, help alleviate that extremely high starting current. And then an addition of a run capacitor to give it a little bit better running efficiency with these larger compressors. So currently Embraco goes up to 2 horsepower, but I believe in 115 volt, it's only 1.5 horsepower. So you're always going to see a CSR motor in that type of application. And then above 1.5 horsepower, you're going to see, you'll start to see some 3-phase motors, and especially in air conditioning, where you get above, a 3-ton or a 3 horsepower compressor, you're going to see 3-phase. And these are characterized by 3 leads of power, each slightly out of phase from each other. So this alleviates the need for starting components, because the power is slightly out of phase, and that gives it the rotational force to get it going without start components other than a relay. You just need a large heavy duty, not a relay, but a contactor, large heavy duty switch just to turn it on and off. And then the 3-phase power does the rest. These are high starting torque and high running torque by design. So of course you're going to see these on a very large 3+ horsepower compressor motors. Like I say, a lot of your commercial air conditioning technicians are more familiar with this. They're fairly simple as far as components go. So then moving on to testing the compressor. This is talking about testing the hermetic single-phase compressors. And there's two main checks you can do, and the first one is the winding resistance check. It's a very simple check you can do with your multimeter. But before we talk about it, we want to be sure that the power is off anytime the terminal cover is removed. Always be very careful with this and wear safety glasses when testing these windings, because those terminals are mounted in a fusite material. This material, it can get corroded or damaged by acid or arcing inside the compressor, which could damage the terminals. You always want to keep your face to the side. Don't put your face in front of these terminals when you're checking them, because if you touch these terminals, wiggle them around, and they blow out from being corroded, it will vent system pressure. And it may only be 50 or 60 PSI of pressure, but if you've ever been around this, you're going to know it's fairly violent, and it makes a pretty good pop. You don't want to have your face anywhere near that when that happens. So make sure we have the power off and wear our safety gear. And then basically we're going to verify the ohmic resistance through the compressor windings. You're just going to read common to start and common to run and compare it to the manufacturer spec sheet. So if you have the Embraco compressor and spec sheet in front of you, you can look at it up here in the wiring diagram, and you can see the layout of the terminals. It's going to give you the common run and start, which one they are. If we don't have the spec sheet, we have 2 different layouts. On your F and EG models, you're going to have the common on the bottom. And try to remember to go clockwise from common. So common's going to be on the bottom. Going clockwise to the top left, you have your run winding. And then top right, you have your start winding. And then all other models, except for the three-phase DC, you're gonna, the EM, NBs, NEs, NEKs, NEUs, NTs, NJs, you're gonna see common on top. And then again, going clockwise, you'll have your run winding and then your start winding. So try to remember that that clockwise trick. It'll help. You got common, then going clockwise, the next terminal should be run and the next terminal should be start. So then we can read resistance through the compressor motor and compare it to the spec sheet down here on the right. As you can see, the run winding on this, I believe it says 1.55 ohms, and that's plus or minus 8% at 77 degrees. Just remember, if you've got a very hot compressor, you're going to have a higher resistance reading. If you have the ability to let that compressor cool off, maybe come back and check it and see if it's closer. If you get one that's out of range, let it cool off, see if it's closer when you come back. It's very possible to have one that's showing a bit out of range, out of that percentage, but it still be good because of temperature differences. So we're looking for shorted windings. We're looking for open windings. Any kind of short or anything is going to skew these readings. Of course, you can read from start to run if you'd like. Basically, all that's doing is you're reading through both windings. So you're gonna have the sum of both resistances. There's really no need if you read from common to run, common to start. That's kind of going to tell you if the compressor motor is good or not. So the second test, basically, we call it testing for a grounded compressor. What you're really doing is you're reading the condition of the insulation around the windings. A lot of people like to use their multimeter for this, but it's not recommended. It's recommended to use a megohm meter. The reason for this is this meter is going to put a very high electrical load on the windings, and it's going to read resistance in millions of ohms or megohms. And this is going to really test that insulation out. It's going to put a very high load on the windings and test that insulation out and read for minute leakages of current to the compressor body. And it's a very simple operation. Just connect one lead to the terminal and one lead to an unpainted surface of the compressor body. Hit the button and look at the LEDs. It's going to give you red, yellow, green, yellow, or red at a certain, below a certain megohm reading. And if you might have a compressor that's still running, but you might read it and it might be in the yellow. It could even almost show red and still be running. If you find this, you're going to want to go ahead and let the customer know that the insulation is breaking down on this compressor, and they could very well have a short, have a compressor go to ground and quit working, very soon. It's a good indication that a compressor is getting ready to go out. So very, very good tool to have on your truck, the megohm meter, to test compressors. So moving on to the electrical components that we use on these types of compressors, we have a current relay, which is very common. We'll talk about the differences in that. We have the PTC relay, which is a solid state relay with no moving parts. Terminal covers are two different types of overloads, and then two different types of capacitors. So that current relay, it's very common, and it's you can tell it's a current relay by looking at that heavy copper wire wrapped around the body. It's basically the coil of the relay. It's normally open, and how it works is it closes when it senses, when the compressor starts, it senses the heavy inrush current through the run winding at startup. And as this coil senses that inrush current, it's going to pull this plunger in and energize the contacts of the start winding. So, like I said, it's normally open. So as soon as that compressor starts up and that heavy inrush current falls off to normal running current, gravity is going to pull this plunger down and de-energize the start winding. So it's a very simple device the way it works. You see this a lot because it's so simple. But basically, if we find one of these and we want to test it, you can pull it off the compressor, and being that it's normally open, you can test the run and the start terminals that plug onto the compressor. It's normally open, so in the mounted position, with the relay in the mounted position, there should be no continuity. If there is, the contacts could be stuck. Then turn the relay over and check it again. The contacts, gravity should cause the contacts to close, and you should have continuity. And then if you test the coil on terminals 1 and 2, you should have continuity. If not, you've got an open or damaged coil. Then we have the PTC relay. Like I said, it's a solid state electronic. It's not electronic, but it's a solid state relay. And the way this works, it has a pill that's made out of a material that has a positive temperature coefficient, meaning that when the compressor tries to start, it's got a low resistance, and it lets current pass through the start winding. And once that current starts to pass through this pill, the current very quickly causes the temperature to heat this pill up, which at the same time causes the resistance to go up, effectively cutting off current to the start winding. So when it starts, it allows current to the start winding. In a split second, cuts off current to the start winding and leaves the compressor running on the run winding. Also a very simple device. And the way to test these, you can either find the chart like this, which is in Embraco's compressor application manual on their website at embraco.com. But basically, you're going to test the resistance, the ohmic resistance through terminals 2 and 3, and you can compare it to this chart. Or you can just test it and see that you have some resistance. If you don't have any resistance, it could indicate that the pill is broken or damaged. And also sometimes they'll smell burnt. If you have like high current, it'll burn up that pill, and they'll kind of smell burnt, and you can tell they're bad that way as well. So then there's also the voltage or the potential relay. And this relay works off of voltage, and it works in a way that when the compressor starts up, well, one thing about this relay is it has normally closed contacts. And so when the compressor starts up, the start winding is energized. The start circuit is closed. And so the compressor starts up. When it gets to 75% operational speed, there's a coil inside this relay that starts reading a voltage that's generated by the start winding. We call it back EMF, or electromotive force. So as that compressor spins up, it starts generating a voltage off the start winding. This coil reads that EMF, and when it gets up to about 75% speed, it's designed to open the contacts, to lift up the contacts, and that's what they call pickup volts, because when that coil senses enough voltage, it'll pick up those contacts and de-energize the start winding. And we see these on the CSR motor types, the larger compressors, because it's got that advantage of having a normally closed contacts. So there's less potential for arcing at startup. So this is a look inside that relay. You can see that magnetic coil that senses the back EMF. When it gets enough back EMF to this coil, you can see it pulls this armature in, opening these contacts and de-energizing the start winding. And the way we want to test these, you need correct voltage, and that would be on terminals 4 and 5. You need line voltages there. If not, you need to figure out why. Then we can disconnect power, remove all connections, and check continuity between terminals 2 and 5. If none, that means the coil is open, and we're going to have to replace the relay. Then check continuity on terminals 1 and 2, And if none, the contacts are stuck open, excuse me, because this is a normally closed relay. So we're going to have to replace the relay at that point. And then we have our overload protectors or thermal protection devices. These are designed to protect the compressor motor from any kind of overload, mostly heat or high discharge pressures, things like that. But they're designed to be an on-off device to disconnect power to the compressor in the event of an overload. And the way they do that, your typical one is the 3/4 round, also called the Klexon a lot of times. They have a little heater wire underneath the contacts, which are mounted on a bimetal piece of metal here. And that heater, when you sense heavy current through that wire there, it's going to heat up. It's going to cause that bimetal to deflect and open the contacts. And given some time to cool off, it's gonna snap back down, and it's going to close again. So it's a basic continuity check through these devices. The 4TM is a little bit, it kind of works on the same principle, but it's a more compact overload device. But you actually have, this is the heater here, you actually have the same little bimetal with contacts on it that deflects. It's just very compact. It's almost flat. But these are the two types of overload devices you'll see on our small hermetic compressors. And this is a look inside the 3/4 round. You can see the bimetal with the contacts on it and the contacts surface here, and you can see the little heater wire in it. Then we have two types of capacitors. We have start and run capacitors. And basically, the start capacitor is not designed to be held in the system, but just for a split second, just on startup. If you get a sticking relay, you're going to burn up that start capacitor very quickly. So if we have like a potential relay with where the contacts have welded, you can check amp draw on the start winding of the compressor to see if that start winding is being de-energized. And if not, you got to change the relay, and you're probably going to have to change the start cap too, because they get burned up very quickly. They're only meant to be in the circuit for that split second startup time. And then we have run winding, a run capacitor. And these are designed to be in the circuit at all times to increase running efficiency. So the way they're designed, they can be energized all the time. And basically, as we stated before, the start winding gives us extra starting torque, and the start capacitor and the run capacitor gives us additional running torque and efficiency. And you can check these. The best way to check these is with capacitance on your multimeter. And just make sure that they at least get up to the microfarad range that's stated on the shell, and they should be good. Now, they do wear, so you do, want to check these. They do wear over time and may not be able to get into the correct microfarad range. So it's important to go ahead and check those whenever you can. So now I'll move on to some common problems you might see in the field. One of the problems in the field that we like to talk about is safety. People doing things in the field that that aren't taking into consideration their personal safety or also the safety of others around them. You want to always be cognizant of everything you can. Try to realize unsafe situations. If you walk up to a job site and you see, I don't know, where you got to work, you see a whole bunch of boxes, heavy boxes stacked up above where you're working, that could fall on you, any kind of thing like that, you want to be very careful and use all our protective gear. And we have to do this because in refrigeration, there's a lot of electrical danger, and, there's pressurized equipment. There's a lot of things to be thinking about. Unlike this fellow, I'm not sure if he's thinking about safety right now, but he's braver than I am. That's all I can say. So another problem in the field is misdiagnosis. And Bracco tells us that over 50% of the compressors returned from the field actually have no defect. When we do a run of checking compressors, warranty compressors from the field, this is what they're finding. They throw them on the machine, and the compressor starts and runs and is working perfectly. This just means that better diagnosis should be done, for a couple different reasons. I mean, we don't want to change a compressor that we don't have to, for the extra work of it, and we also don't want to, charge a customer to change a compressor that may not need to be changed. So we also see a problem with low voltage in the field. A lot of times in commercial environments, you see where you might have had a dedicated circuit or a piece of equipment on one circuit, and then another piece of equipment was added. Then all of a sudden you get startability issues. This slide just shows the minimum guaranteed start voltage. We use the G code, which is 115 volt. As you can see, the minimum start voltage is 98 volts. So you can put your meter on it when the compressor's starting. If you got an intermittent problem, make sure you're not dropping below 98 volts when that thing starts. And for the other one is D voltage, 208, 230 volt. Make sure it's not dropping below 177 volts. And then, of course, there's maintenance. We see a lot of this, just plain a lack of maintenance, either by not knowing or, people, don't want to call for service. They don't want to pay the service technician to come out and maintain the system. Obviously, especially in a commercial environment, you're going to see this type of buildup on the condenser coil. And then, your system can't reject the heat anymore. So it's just going to sit there and heat soak. It's going to heat up the oil. It's going to get the oil so hot, and the compressor is going to be so hot, it's going to cook the oil inside the bearings, and you're going to get all kinds of debris, and the oil is going to get cooked on the bearings and everything. It's going to cause all kinds of problems. Your valves aren't going to seal good anymore, and then it's all downhill from there. And and if it gets too bad and it runs like this for too long, it may not trip the overload. And then the technician finally goes in there and he cleans all this up, and you've degraded your oil so bad that it broke down and clogged up the cap tube. So obviously very important to do a good job of maintaining this equipment. Keep the coils cleaned and this and that. So one of the problems that it's not talked about too much, but you could have some oil that has left the crankcase and has gotten trapped out in the system. For whatever reason, the compressor's going bad. You got, dirty coils, and you could get some oil trapped in the evaporator or the condenser. And what's going to happen is when you go put the new compressor in, you get normal pressures going again. All of a sudden, a big old slug of oil is going to come back to the compressor and hit the valves, break the valves, or it's going to, overfill the crankcase and cause problems. But it is recommended to pour the oil into a container and measure it and make sure it's within plus or minus 2% of what's listed on the spec sheet. If we have less than that oil that came out of the compressor, it's recommended to go ahead and flush that system with some system flush. Make sure we get all that old oil out of there. Plus the oil could be contaminated with acid and moisture, and it could also tear up the windings of the new compressors in very short order. So moisture and contaminants can be introduced into the system through poor piping and service practices. We want to make sure we're purging nitrogen when we're brazing at about 2 psi. This prevents the black oxide formation on the inside of the tubes. In the old days in air conditioning, when you're using mineral oil is very forgiving. That oxide may stay put. But with the new systems with POE oil is like a solvent. It's going to scrub these contaminants off the inside of the tube, and it's going to clog things up. And then after we braze, we want to make sure we pressure test with nitrogen. Make sure that everything's not leaking. This also absorbs any excess moisture. The nitrogen is going to help get any excess moisture out of there. I want to change that oil in that vacuum pump before every evacuation. A vacuum pump is not able to pull a good vacuum if it's got dirty, moisture-laden oil in it. It's not going to be able to really get a good vacuum on that system. And we really need to verify that vacuum level with an electronic micron gauge. We want to see 500 microns or less and pull it for 20 to 30 minutes at that. And that should ensure that you're getting all the moisture out of there. And about that dryer, definitely want to change that dryer. I don't think anyone's ever reusing an old dryer, but if anyone's ever thinking about it, definitely don't do that. It can only absorb the moisture once, and it's saturated. We want to make sure we size it correctly, not too small, and and also don't put a giant dryer on a tiny system that can hold almost the full charge in the dryer. And that's basically it. The dryer protects the system from any excess moisture that's left over from the evacuation process and debris. So it's very important. And then we see improper refrigerant charges. We always want to weigh in the charge whenever possible. It's basically mandatory with these very small systems that have real tiny charges. If we're using a blend, need to charge that in liquid form so we don't fractionate the blend, because you can actually get more of one molecule than the other, and then you don't know what you have in there. The system's not working correctly because the blend is not at the right ratio. And you can also account for the refrigerant in your hose. It's about 0.3 ounces per foot for a 1/4 inch hose, and 0.7 for a 3/8 hose. That's for R22. It's going to be a little bit different with different density refrigerants. Basically, if you measure the correct charge through your scale, and then you close off your valves and start up the system, you can meter in the rest of the charge through the charging and the suction line, and that should basically ensure that you're getting almost the exact charge in there. And you can also verify it with either superheat or subcooling. We'll talk a little bit more about that in a little bit. Like right now, what is superheat? So any superheat is any increase in the temperature of the refrigerant above its boiling point is what we call superheat. We also call that boiling point the saturation point. So anytime a liquid it gets enough heat in it to where it boils, that's what we call the saturation point. And you can use that to charge a system. Typically, we're going to want to use superheat in a fixed orifice system because we'll talk about that in a second when we talk about subcooling. But basically, that's what superheat is. We measure the temperature of the refrigerant above its boiling point. And then there's subcooling, and that's any decrease in temperature of the refrigerant below its condensing or saturation point. So any temperature measured between the condensing point and measured at a point in the system, you're going to call that subcooling. And we're going to use subcooling typically for systems with TXV valves. We'll talk a little bit more about TXV valves in a second. So when we're checking superheat, I apologize that we show a TXV valve here for checking superheat, but you can check superheat on a TXV valve to make sure it has the correct superheat. In commercial systems, there's a lot of TXV valves that require adjustment, and you may have to set superheat on a TXV valve. But basically, what we're going to do, we're going to check our low side suction pressure, and then measure the suction pressure. We're in this system, we're showing 20 psi G gauge, and then we're going to use a PT chart to convert that to the saturated temp, which is 22 degrees. And then we're going to measure the suction line, and then we're going to minus these two temperatures, and that's going to give us saturated temp. Yep, on this system, we're going to have 10 degrees of superheat. And for typically, kind of as an average, I like to say on a low temp system, you're looking for about 6 to 8 degrees of superheat. medium temp 8 to 10, and for air conditioning 10 to 12. Now that's measuring the suction line right out of the evaporator. If you're measuring the temperature of the suction line at the compressor, you're going to be looking for about 18 to 20 degrees of superheat. And that's going to guarantee us that you're not getting any liquid refrigerant migration back to the compressor. So measuring out of the evaporator is where you're going to get those lower readings, and measuring at the compressor, you're going to be looking for 18 to 20 degrees. Now that's in an air conditioning application, so you may or may not be able to measure at the compressor in refrigeration. You may have more access to measure coming out of the evaporator. But basically what you're doing is you're measuring the temperature from the point of complete vaporization to this point right here on the suction line. So if we're the lower your superheat, the more excess of refrigerant, the more refrigerant's making its way through the evaporator. So if you're measuring superheat at the compressor and you get 5 degrees of superheat or even 0 degrees, then you're getting liquid refrigerant returned to that compressor. Could be several different reasons. You could have a blower motor that's not working well. You could have a dirty air filter, anything that's causing low airflow, excuse me, low airflow across the evaporator. So this is an example of a charging chart that a manufacturer might include on a condenser, on an air conditioning condenser. And these are really good to use because on different days, maybe on a cooler day, you can use the parameters on this and get a really good idea of where the charge is at. Some of these require the use of a wet bulb psychrometer or a electronic psychrometer. Some of them you have to plug in wet bulb, but these are a really good idea either on a heat pump or if you're checking an air conditioning system on a cold day. So a little bit about some service procedures. If we're when we're charging a system, an undercharged system, what it's going to do is going to starve the evaporator, reduce suction pressures, and increase return gas temperatures, which is going to overheat the compressor, and it's going to cause inefficiencies and possibly cause a compressor to fail. And obviously, we're not going to have enough refrigerant in the system to do the job of cooling. So an overcharged system is going to cause high discharge pressures, reduced superheat, which means liquid refrigerant flooding and potential compressor damage, because we don't want any liquid refrigerant to enter that compressor. When we're charging the system, the amount of charge and type of the refrigerant should be listed on the data plate of the unit. If this is not available, it's recommended to contact the OEM to find the proper charge, because we always want to weigh in that charge after service as possible. It just removes a lot of possibilities for problems when you weigh it in. And again, when we're charging a system, fixed orifice systems are normally charged by the superheat method if we're not weighing it in. And TXV systems are typically charged with subcooling. Heat pumps typically are charged in the heating cycle, really should be charged by weight and then checked by subcooling, because pretty much all your heat pumps use TXV valves now. Speaking of TXV valves, so we say that you want to use subcooling to charge a TXV equipped system. And this is because TXV valves have the ability to close or open the orifice, metering more or less refrigerant to the evaporator. This means that they can compensate for a little too little or a little too much refrigerant. So they're actually attempting to maintain the correct superheat, meaning the correct amount of refrigerant to the evaporator. And they do this by mounting a vapor bulb, a sensing bulb, on the suction line coming out of the evaporator. This senses the heat load that's on the evaporator, and the higher the heat load, the more it's going to increase the temperature, and then cause this refrigerant that's in the bulb to vaporize and put more pressure on the top of the TXV valve on the bellows, which is going to cause it to open. We have one opening force, which is the bulb pressure, and we have two closing forces, spring pressure, and we have evaporator pressure trying to close it. And so here, this is basically the throttle of the TXV valve, the vapor bulb, causing it to open or close and meter the correct amount of refrigerant to the evaporator. And they're very efficient. That's why most of your manufacturers are going to them now, because they're very efficient at giving the correct amount of refrigerant even in low load conditions, whereas a fixed orifice is just going to be feeding the same amount all the time. So talking about that bulb being the throttle of the TXV valve, we want to make sure it's mounted correctly. Most of your manufacturers are suggesting 10 and 2. We never want to mount it on the bottom where oil or liquid could be giving you a bad temperature reading. So either 10 or 2 is typically where you want to mount it. If you have a weird application where you're adding an aftermarket TXV valve or something like that, it's highly recommended to contact the manufacturer of the TXV valve and ask them for a recommendation where to mount it. Typically, you want to put it on a horizontal tube. That being said, I have seen them mounted on vertical tubes as well, but that's why I say contact the manufacturer and talk to them about the application to make sure you get that bulb mounted where it's supposed to be, because it needs to sense a good, accurate temperature reading to work correctly. And always use the clamp that comes with that bulb. You want to have a very firm clamping between the bulb and the suction line. And if you got a dirty suction line, sand it down, get some nice clean copper. We want good transfer of heat between the bulb and the suction line. And you always want to fully insulate that bulb, because we only want to read the temperature of that suction line, not ambient temperature. And here's an example of someone who did not use the correct clamp. I'm hoping he lost the clamp and he just made do while with what he could, and he's coming back tomorrow to put that clamp on and fix it all up. But this is going to cause problems. It's going to loosen up over time if it's not already loose. It's not going to get a good reading of that suction line, and it doesn't look insulated well. So that means ambient temperature is going to affect that bulb. It's going to tell that bulb that the suction line is warmer than it really is, which is going to cause the TXV valve to open wide open. And in a low load condition, if you have a low load condition outside, but you're still a little warm in this attic or wherever this room is, you're going to start feeding too much refrigerant to that evaporator and not have enough heat load to evaporate it. And guess what? You're going to get liquid refrigerant returning to the compressor. So this is why it's very important to mount those bulbs very securely and insulate them well. If you do that, TXV valves are very reliable and operate very well. So this is just a little refrigeration check summary. This is kind of something I used to do when I was in the field. It's a good place to start with the power supply. Check the fuses, breakers, the wiring, and the control voltage. I always like to start there because I may have started changing out a thermostat one time before I ever found out there was a bad fuse. But anyway, then go to your air delivery, check your filter, your ductwork, your condenser and evaporator, make sure they're clean. Go ahead and hook up your manifold on the high and the low side. If the system runs, go ahead and put a clamp on amp meter on the common of the compressor. Start and observe the pressures and the amp draw. And then use superheat and subcooling to check and see if we're we're evaporating and condensing correctly in the refrigeration circuit. And then use manufacturer specs to check for the proper amp draw on all the motors. If we suspect there could be acid in the system, You can always use one of those 2-second acid test kits that they sell at the supply houses. They're very handy. If the system won't run, go ahead and check the compressor windings and the electrical components. Make sure everything's tight in the electrical department. And basically, this is just using the system approach to service calls for accurate diagnosis. So we're not changing out good compressors and sending them back to Embraco. So a little bit about Embraco's digital tools that we have available. Basically, we have the Embraco website. It's called the product selector, and you can go to embraco.com, click on the product selector, and this is basically, it took the place of our electronic catalog, but you can plug in models and find spec sheets, wiring diagrams, components, a lot of different things on there. It's a very handy resource. We also have a blog for refrigeration technicians through the Refrigeration Club. You can see the website here, http refrigerationclub.com. Basically, refrigeration technicians can go and talk about all manner of things refrigeration. And then we have the product selector software, which is basically the website, the product selector that I was talking about. And it was updated. It's been updated recently, so it has a lot more compressors on there. And then we have the Toolbox app that's a free download on your phone, and it has troubleshooting. It has cross-references information on it, lots of different information about our models and different things like that. Very good tool, and lots of good information on that as well. So I believe that covers the presentation for tonight. I'm going to open it up for questions.
Thank you so much, Danny, for sharing this important content with us. Very detailed and very helpful for the day by day. We have over 100 people connected live, so thank you guys for joining us today. We have very interesting questions here on the chat and also on the landing page where people registered to attend the webinar. So I will start with the question from Sarbij from Canada. What's the cause of compressor grounding?
So basically, that's when your insulation breaks down, it gets damaged, or it gets just a break in it where the current can go from the windings to the compressor shell. And one big cause, well, there's two big causes that I would say. One is overheating of the compressor. The windings get really hot, and the wire can handle it, but the insulation is going to get broke down and get weakened. And so if you get, an overheated compressor, you're going to break down that insulation, and it could either go ahead and cause the compressor to go to ground right away, or it could be a future failure, a short to ground.
Okay, thank you. And another question from Jonathan from Mexico. What's the best way to determine bad valves on a small 1/3 horsepower compressor?
So probably your biggest failure mode when you have bad valves is you'll have a running compressor, but you'll have equalized pressures. You're not creating any suction pressure or discharge pressure. That's probably the biggest indication of bad valves. You can also see sometimes if you have a discharge valve leaking back into the low side of the compressor, you'll have a low discharge and a high suction. You also see that quite often when you have valves going bad.
Mm-hmm. And another question from Dylan in US. Why are so many different types of start relays and overloads? What makes them different? And can you swap out relays and overloads, or does it make a big difference to have the exact replacement?
So that's a good question. I guess it just depends on the type of system. If you have a real plain Jane system with an RSIR motor with a cap tube, you're going to see the current relay predominantly. It's just a very simple, reliable device, and that's probably why they use that mostly. And then when you move on to a residential compressor, where they want to add a run cap, you're going to see that PTC relay because it's just so simple. There's no moving parts. You know, as long as that system is running correctly, I mean, they last a really long time. You know, it's very efficient with a run cap and a PTC. I would say they figured out what works on certain systems and they stick with it. You know, that being said, you can use aftermarket start components. We usually only recommend them when you can't get a hold of the factory components. These 3-in-1 start kits, they can be used, but we recommend them for only temporary, just to get a customer up and running until you can get the factory components. The factory components are tuned specifically to the amp draw, especially the overload to the amp draw of the compressor. That's the main problem with these generic parts, is the overload is tuned for maybe 2, maybe even 3 horsepower motors, and they could either you know, have a nuisance trip where they trip too soon, or they could not trip soon enough and let damage happen to the compressor before they remove the power.
Mm-hmm. Understood. And another question from Neil Hadje. I don't know if I pronounced it correctly. You mentioned damage to the suspension system. Are you saying that if we hear the motor clank against the shell during moving, that the suspension is compromised and the compressor shouldn't be used?
So if you're picking the compressor up in your hands and you hear it clank, that's no problem. That's completely normal. That just means you're going beyond the design of that suspension system. You're going to hear that when you move the compressor. But if the compressor is mounted in the system and just from normal operation, you hear clanking inside there, that means either you have bent or broken springs in the suspension system. It may or may not. It's probably going to keep running for a long, long time like that, because sometimes they can get just a little bit tweaked and there's not a lot of space between the crankcase and the compressor shell. So, you know, it usually runs into a point to where, can the customer handle that sound? And a lot of them can't. So, and unfortunately, there's no way to get inside there and fix that. The compressor has to be changed at that point. But yeah, that's usually what it is. It's a bent or broken spring.
Okay, but the clank is normal.
Yeah, it's normal when you're moving the compressor around with your hand. Okay. Excuse me, sorry.
That's fine. And another question about the loud noises from Joel and from Canada. What happens when cooling unit's temperature goes high and the fan is loud?
Sounds like to me like either an evaporator or a condenser fan could be damaged or malfunctioning, and probably more likely the condenser fan. So if the condenser fan is damaged and it's not spinning fast enough, or the actual fan blade is damaged, you're not moving enough air across the condenser, so you're not rejecting the heat out of the system. So the system's just going to sit there and heat up. That's probably what's going on there.
A question from Amini. from Spain. You see, we have a lot of people connected from Europe. I saw Ireland before. So, Emily, why HP is never in the compressor technical data sheets? Is there a reason for not disclosing HP?
Well, I will tell you this. In our spec sheets, the horsepower is in there. Now, I will say this: horsepower is it's very broad and it's not very accurate. It just puts you in the ballpark of what a compressor is, because you could have a 3rd horsepower compressor that has 950 BTUs, and then you could have a 3rd horsepower compressor that has 1200. So it just puts you in the ballpark. But it's a very generic, maybe an old-fashioned way to rate a compressor. I would never recommend using just horsepower to, cross a compressor. I always go by BTUs at the correct rating point.
Yeah, that's important. A question from Robert D. Do you backflush the oil out? Can you do that?
When you're flushing a system, typically, if I'm not mistaken, most of the flushes ask you to flush through the liquid line, flush the same direction as the refrigerant flows. And they ask you to do that because you're flushing, through the liquid line, through the evaporator, and then when you hit the suction line, the tubing gets larger and gives the flush more of a chance to evaporate and come out of the system better. So I think you can do it either way, but I would recommend doing it like they say, going through the liquid line, through the evaporator and then out the suction line. And you really only want to flush the line sets. You don't want to flush any components. So if there's any components in there, like a TXV valve, you want to remove it, and don't flush a compressor. And then they say collect everything in a bucket that comes out. But that's really, I think, the recommended procedure that they say. And of course, you're going to follow it up with a lot of nitrogen to make sure you get all that solvent out of there.
Mm-hmm. And you mentioned about the TXV valve. We had a question about the acronym. Can you use the TXV and TEV as well for thermal expansion valve?
Yes. Yeah, that's pretty much the same, just different acronym, but it's the same. The only thing would be different is sometimes you see an electronic expansion valve. So I think they call them EEC. So that's really the only thing. Sometimes you'll see an electronic expansion valve, but TXV and TEV should be the same thing, thermostatic expansion valve. The X just standing for expansion. And I believe there's another one called an automatic expansion valve that has a very set specific way that it operates. But TEV, TXV is the same thing.
Okay, thank you. And one more question from Kwei. How often is it for small household compressor to get locked or seized?
To get locked up or seized up?
Yeah.
So when you have a compressor that locks up, it's usually from a lack of lubrication. And that lack of lubrication could be from for some different things. You could have a system that's overheated and degraded the oil. You could have some migration of refrigerant to the compressor, and it'll mix with the oil. And when the compressor starts, it'll cause basically when the compressor starts, the refrigerant is inside the oil and it comes out of the oil. When it does, it evaporates and flashes off. It brings the oil with it, takes it out of the system, and it may take 2 or 3 minutes for it to return to the crankcase. So there's a lot of different reasons that can happen. But I would say if you got a compressor or a refrigeration system that's well maintained, you keep all the coils clean, you check on it and everything, make sure everything's running good, the compressor may never seize up. It may work for 20 years, and then a winding may open or something else might happen. But yeah, there's really no set time for a compressor to seize up. It's designed, basically, if it's well maintained, to work for a really, really long time without ever locking up.
Okay. Unfortunately, our time is already past.